Today we're going to show you a wacky water experiment that I think is really clever. The first step is to put your cold water jar inside your dish, then carefully cover it with the plastic card. The next step is to turn this jar carefully upside down. You'll see that the vacuum formed inside the jar holds the card onto the surface. Then have your mum or dad place the hot jar of water into the dish and carefully place the cold jar on top. You'll need to go around every side of the jar and make sure that the edges line up perfectly. Then get someone to very carefully pull out the card from in between the jars. As they do, you'll see that the water starts to mix, which forms a pinkish purple colour. As each of the jars mixes in with the other one, you'll see that the colour evens out completely. This is because the water is very slowly mixing all of its molecules together. Now try this. Take the jar of red hot water, place the card on top, and repeat the same steps. This time the blue jar is on the bottom and the red jar is on the top. Have someone very carefully remove the card from the middle, and this time you'll see that the jars don't mix. So why is this? Is it the colours? No, it's not. In fact, the hot water has a different density to the cold water. It's very slightly less dense than the cold water and so sits on top. When we compare them side to side, you'll see that the reaction is completely different. This is because the cold water in the first experiment is more dense than the hot water, and so sinks more dense than the hot water, and so sinks more dense than the hot water, and so sinks between the molecules in the hot water. And there we have it, a really simple, really cool science experiment.
Look at that. The iron anvil floats because mercury has a density nearly twice that of iron. In fact, due to the density ratios, the iron actually floats better than wood does in water.
Push something.
Let's push it down. Oh, it's hard to push down. Oh, that was great. Here, let's try it again.
However, if you look at the egg, you see that it is not suffering from being squashed, pushed or pulled by any forces. It is simply at rest, at its equilibrium with the surroundings. You see, you need not be falling through infinite space to be weightless. There is only ever a downward or upward force if the equilibrium is disrupted, like stretching an elastic band that snaps back to its natural state when you let it go. So here we see the egg is in fact weightless. It is more or less a part of the water at an equilibrium, equal density.
If we make the air around the helium less dense than the helium inside of it, then the helium balloon should sink. And so when I turn on my vacuum chamber, the balloons will expand, and what I'm going to try to do and hope for is that they'll expand, but the balloon will keep it pressurized enough so that the outside air will be less dense than the helium inside of it. And at that point, the helium balloon should fall. Okay, helium balloons in a vacuum chamber. 3, 2, 1. They're gonna fall. Trying to turn it off right before they pop. Oh, that one fell. See? Stop floating. And... oh, they both fell. Look at that.
Two scientific experiments that were conducted in a vacuum chamber. I'll link these videos in the description, all credit to Cody's lab. This first video proves that thrust is not possible in a vacuum.
Welcome back to Cody's lab. So as you can see, we're using the vacuum chamber once again, and I actually have a little feather right there, as you can see, suspended in front of a 12-volt electric fan. See, I got the batteries, a pressure gauge, and everything in there. To turn it on, I have a little tilt switch, says magnetically controlled. You can see when I turn the fan on, it blows the feather all over the place. This is, of course, at atmospheric pressure right now. So, I want to take this down to Martian conditions. You might have noticed the Martian reference over there. First thing I'm going to do is add a little bit of dry ice to the chamber, just so that the atmosphere gets replaced with CO2. Many of you guys were complaining about that last time. So now I should have a CO2 atmosphere, or at least it'll create one. And now we're going to suck out all of the air, or at least most of it, down to the point where about between 4 to 6 millimeters of mercury, which is, of course, the pressure on the surface of Mars. So let's plug in the vacuum pump. There we go. Give this a little while to suck down. These pieces of CO2 look really interesting in the vacuum. The gas produced causes them to levitate and float all over the place. But if you can see the gauge over there, you can see that the air pressure is just about to the point where it's would be considered the surface of Mars. So since we're at Martian air pressure, let's unplug the vacuum pump and let's turn on this fan. Place your bets as to what's going to happen to this feather. Now the fan's only going to produce maybe 10 miles per hour worth of wind. On the surface of Mars, the fastest recorded wind speed is about 70 miles an hour. But let's say the superstorm in the Martian had wind speeds of 200 miles an hour, 20 times what we have here. To compensate for that, I imagine the feather is about 20 times easier to push over than a spaceship. So let's see what happens. Okay, fan's on. And the feather's not moving. In fact, let's zoom in on that.
This second experiment proves that combustion is not possible in a vacuum.
So how about something that has its own oxidizer, such as gunpowder? See, this is a mixture of charcoal, sulfur, and potassium nitrate. When heated, the potassium nitrate gives off oxygen, which the sulfur and charcoal uses to burn. So I've got a little bit sitting in there. Let's apply the laser goggles, and let's light it off. First in the atmosphere, and then in the vacuum. Okay, as you can see, it produced lots of smoke and burned rather quickly. Most of the air is now gone. Let's see what happens. The gunpowder did not ignite. I saw some smoke coming off of it, so I know it burned a little. Let's try again more in the center of the pile. And that's it. The gunpowder does not burn. And so I'm going to be burning some rocket candy. This is a mixture of sugar, potassium nitrate, and iron oxide. This is used in amateur rockets because the ingredients are readily available and the amount of thrust it produces is quite high. So let's light this on fire and see how it does. So this is in Earth atmosphere. As you can see, it burns rather rapidly, producing a little bit of thrust even. As you can see towards the end, it moved it around. So now let's try it inside of a vacuum. No ignition. That's interesting. I did see some little poofs as it tried to burn, but it was unable to sustain itself. So even when it's in one solid piece, it can't chain and continue burning. So I've let a little bit more air back into the chamber. Let's see if it'll burn now. That's a no-go on burn. Wait. It's kind of smoldering. And it's out. Acetone peroxide in the atmosphere in 3, 2, 1. Yes, that's a little bit more volatile than gunpowder is. Acetone peroxide in vacuum in 3, 2, 1. It still didn't burn.
So essentially, what we have here is solid evidence that space travel is fake.
You know, how are there satellites and a space station in the thermosphere layer of the atmosphere when the temperature gets up to 2,000 degrees Celsius? And that's when everything clicked.